a quick review for the exam. Now let's go back to the beginning. We talked about this energy separation. We say that for a qubit, for example, a superconducting qubit, the energy separation is very tiny. For example, in this case, it's only 0.02 milli eV. And of course, you understand why we need to go to cryogenic temperature, because the thermal energy is kT. Another hint, you need to know how to do kT, right? That's one thing, right? Then we talk about the transistor equation. You're supposed to have learned it in E221 or we did not have 222 recently. But the main point is that at lower temperature, you have higher current, right? So that is a common sense. We also talk about the subthreshold slope. What is the meaning of subthreshold slope? Right? We test a lot in the midterm. I still want you to learn it, right? But we say that there's something called saturation of subthreshold slope. When you go to really low temperature, they just saturate. They do not follow the Boltzmann statistic. It does not go to zero, right? We talk about Bentel states and traps. And this is very important. When we say the transistor has a higher mobility, higher current, it's because it has a higher mobility. So we talk about Tagagi's model, another hint, important hint. Tagagi's model has three important components. Try to model the inversion layer electron, which contribute to the current. What are the three types of scattering? Again, scattering is what slowing down the electron, right? So what are the three types? Yeah, Coulomb, photon, and surface roughness, right? Coulomb is because you feel that impurity, the traps, they have electric field. You feel them, it deflect you, so can you slow down the electron or hole, right? So if at low temperature, do you feel more or less? Coulomb. Do you feel more Coulomb scattering at low temperature or more? More. Why? Not because other people has less than I have more, right? I have less income in other job than I have more income in this job. Yeah. Because you are lower temperature, so you will have a lower thermal velocity. So you stay longer in the field, you get more, right? If you just zoom very fast and leave it, you only feel a little bit, a very brief time, right? So that's why here Coulomb scattering, here, it is not shown here. But if you go to lower temperature, you actually have more Coulomb scattering. Means lower mobility. Okay, don't mess up scattering and mobility, okay? More scattering, lower mobility. How about photon scattering? You get more or less in lower temperature? Less. Why? Less lattice vibration, right? Photon is just because of the lattice vibration. And then you have surface roughness, which not that temperature dependence. You can assume they are not. Here, plotting the electric field versus mobility. When you go to very high electric field, you have a lot of, this is vertical electric field, right? Remember what we are talking about is this. This is Vg, and then we are talking about this E field, right? So I'm walking from this door to that door, but then I have someone keep pushing me against the wall due to electric field. I will walk slower, right? You keep pushing me against the wall. I keep scratching my skin, right? Much slower, right? So that's why when you go to higher electric field, your surface mobility reduces. And it becomes even smaller than the photon scattering. So if I have lower temperature, what will happen to this photon curve? Will it go up or go down at lower temperature? It will go up, right? Higher mobility. Okay, we talk about the field ionization of the incomplete ionization because the trap level is never at the conduction band. It's a little bit lower. At room temperature, we don't feel it. Then we say, okay, all the dopant, right, boron, arsenate, they all ionize. They become free. They have free electrons, but at low temperature, they just trap there. Okay. We also learn about the free cell effect. When you have a very low temperature, all the dopant you say supposed to be conductive at low temperature, actually they are not conductive. Again, just the same as what we say earlier, because they cannot get ionized. Okay. We also have King effect, right? This King effect, or this can cause the parasitic latch up, and that's why we introduce SOI. SOI can block the make the bottom become insulator, so now you have less parasitic capacitors, right? Yeah, and then we talk about different hot carrier degradation and quantum confinement, right? We also talk about HAMT. HAMT is another device that it forms two-dimensional electron gas. The reason is this is very high mobility because the dopant are in the barrier, so you do not feel the Coulomb scattering. Okay. And transit frequency, right? We talk about transit frequency of HAMT and quantum confinement. I don't expect you to memorize this equation. And then eventually we switch to circuits. We talk about the noise. This is very important. You should know that a resistor can have a 4 kTr as a voltage noise, or the Norton equivalent 4 kT divided by R1 if you want to make it a current source, right? But no matter how complicated the circuit is, if you look into the port, the noise generated by this circuit is the real part of this impedance times 4 kT, which is easy to memorize. Okay. We already studied this earlier. I mentioned this earlier. 3 sources of transistor noise: the gate noise, right? Gate thermal noise, the thermal noise in the channel, and the flicker noise. And this is pretty common. People will try to find the corner frequency because flicker noise gets lower at high frequency. And what is flicker noise? The physical source. Yeah, very good. Yeah, so electron get trapped and detrapped. If you remember my analogy, just like an army marching in front of this building. Once in a while, someone from the building pulled one of the soldier in randomly, and maybe before I release the soldier, I pull another soldier. So the army, the current, right, the current of soldier becomes less by 2 people. But suddenly, I feed them, they're happy, then I let them go. Suddenly, you may have 1 extra or 2 extra soldier. And that is how you get the flicker noise. And how fast can I pull the electron back and forth? Cannot be too fast because it's a mass, right? It's always difficult to move the mass in the real space. And that's why I cannot do this in terahertz or 100 of terahertz. That's why the noise at that frequency is small. But they are tends to be very large at very low frequency, right? Input referral noise, I already gave you the hint, right? What is that? It's just that if I want to find, I have a noisy circuit. I want to model it as I have a noise in the input, but it is a noiseless circuit, so that the output has the same noise, right? So here I may feel Vn out square. Here I also feel Vn out square. These two should be the same when I model it. Okay. And then here comes to the noise figure. That's what you said earlier, right? You either just take the total output noise, which include everything, and then divide by the gain reference to 4 kTr. Or you have a 1, but this time you only take the noise generated by your circuit divided by everything. Right? So we have done the same thing today. Not today, actually, today we break it into 3 parts, right? 1, noise by the resistor, and the noise by M1. Okay. Say again? They are equivalent. Yeah, you need to be proficient in both. It's easier to answer. But they're equivalent. But I think you need to learn the basics, know how to do the assignment. My exam is always easier than assignment. So don't worry too much, okay? Then we say that we might have multi-stage of amplification. And what we want is to have a low noise figure in the initial stage, because those from the later stage got diminished by the available power gain. Right? It's not the exact gain, but it's the available power gain. And yeah, so that's the last summary. We start with, it's good to have a table. We start with the common source amplifier with amplifier to do the matching. We say, why don't I just add a resistor at the input? Too noisy, right? Not a good strategy. So we try to do inductive load, because we showed that by this we actually, due to the feedback capacitor here, I actually can match the input impedance, but sometimes it might oscillate. Okay, and so later we say, then how about we try to do a feedback resistor? We can do that pretty well, and it doesn't contribute to the noise much. However, still high, more than 3 dB or 3 dB, right? So we also study common gates with inductive loading. This is more for exercise and also for your project, because it uses the 1/GM to do the matching. Naturally match it well, right? But it has other problem. Eventually we use cascode, because with cascode it will isolate us from the inductor and also solve the problem that we have here. I should not have today here, right? So, but still not good enough. You did that in the project. Many of you get noise of 6 dB. I also got 4 point something or 5. That's why I said 6 dB, because I randomly designed it. I got 4 point something or above 5. So I think you guys spent 2 weeks to be able to achieve 6 dB, right? Well, some of you got close to 4, but it seems to me maybe just because you have a smaller inductor, because those people have a larger transistor, so they're larger capacitor. Some of them also try to add a large C1 there, and because our inductor actually have serious resistor, so I feel that that's the reason they get lower noise, right? But in reality, when you add a capacitor, although the area is larger, you also have resistor. Yeah, so time's up. And this one you are very familiar already with assignment 4, and finally the matching transformation. Okay, so I will stop here. If any question, please just email me.